Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. In this video, we will discuss solution for several questions of tutorial 3 that has been requested, and I have select the question number 14, 15 and 16 to be discussed this time. For the question, you may refer to your question paper. Alright, so let's see the solution for question number 14 first. So let's say we have one line charge density, and the value for this density is equal to rho L. So this line is reside on the z-axis, and we need to prove that the potential difference between R1 and R2, so given by this expression. Alright, so because of this is involve a line charge density, so we assume that this line charge density will be developed a cylindrical shape of electric field intensity. So therefore, the coordinate system that we are going to use during this analysis is a cylindrical coordinate system. During previous lecture, so we have been derived the expression that represent electric field intensity by considering this shape, whereas the electric field intensity, so vector of E, is equal to R cap rho L divided by 2 pi epsilon naught R. In order to find or to derive electric potential difference equation, so we have this expression, whereas V12 is equal to V2 minus V1, so minus integration from R2 until R1 vector of E dot vector of dl, which is represent the direction of the vector of this operation. And because of we are using cylindrical coordinate system, so the expression that represent our dl is equal to R cap dr. If we put all component inside this expression, then we will have the electric potential difference V12 is given by this formula, minus integration from R2 until R1 R cap rho L divided by 2 pi epsilon naught R dot with R cap dr. By solving this operation, then we will have this expression, whereas negative integration from R2 until R1 rho L divided by 2 pi epsilon naught R dr. So by solving this integration, so we will have, this is our answer, so solution for the integration, whereas V21 is equal to rho L divided by 2 pi epsilon naught, so ln R from R1 until R2. If you solve this operation, then we will have the expression that represent our potential difference V21 here is equal to rho L divided by 2 pi epsilon naught ln R2 divided by R1. So that's solution for the question number 14. Alright, so now let's see the solution for number 15. So we are given an electric field intensity in a spherical shape because of the vector that represent our electric field intensity in a R cap component. So we have the shape of electric field intensity in a spherical shape here, and then we need to determine the electric potential difference between point A, which is located on z-axis, and the coordinate is equal to 2, and the second point is a B point that located on -4 from the origin. Okay, so in order to solve this problem, and because of the electric field intensity in terms of a spherical coordinate system, but our test point is located on z cap component, then we need to find what is the representative of z cap in r cap component. Alright, so let's see here. So along this z axis, so let's consider the A point first, and because of the value for the A is in terms of a positive z cap, so we will have the r cap component is equal to positive z component. So that means whatever value that represent our r is equal to z. Then we will have the vector of E in the z component is equal to z cap, positive z cap, 18 divided by z squared. While on the second point, because of the location for the second point is on the negative axis of z, then we will have along minus z cap, we have r cap is equal to minus z cap. Then we will have our vector E here is equal to minus z cap, 18 divided by z squared. In order to find the potential difference between that point, so we need to use this equation, whereas VAB is equal to minus integration from B to A E dot dl. And because of, in this case, so dl direction of length is given on the z axis, then we can directly represent our vector dl is equal to z cap dz. Then we can put all equation that we have here. So VAB is equal to minus integration from -4 until 2. So r cap 18 divided by r squared z cap dz. And since this expression can be expressed in a z component, then we will have and then we need to perform two different integration. The first integration is from -4 until 0. So this one is on a negative z cap direction, then we will have minus z cap 18 divided by z squared dot z cap dz. So this one is expression for dl, and our second term is equal to integration from 0 until 2. So this one is along a positive z, then we'll have z cap 18 divided by z squared dot z cap dz. If you solve this operation, the answer for the different potential on this given case is equal to 4 volt. Alright, so that is the solution for the question number 50. Alright, now let's move to the question number 16. As we have been derived in a lecture, the expression for electric field intensity vector for the electric dipole case is given by this equation, whereas the vector of E is equal to QD divided by 4 pi epsilon naught r power of 3. R cap 2 cos theta plus theta cap sin theta. If d, which is represent the distance between both charge, is equal to 1 cm, so the expression for vector E is given by this formula. So we just replace the d with 1 cm, then we will have this expression. If r is equal to 1 meter and theta is equal to 0 degree, then we will have the amplitude for electric field intensity is equal to 4 millivolt. By considering all the parameters, and then we put all the parameters into this equation, then we will have the vector of E is equal to this formula, 0.01 q, so divided by 4 pi epsilon r cap 2. And the amplitude for this particular vector is equal to this expression, and at the same time the result from this expression is equal to 4 millivolt. So from this step, so we can directly calculate the value for our charge here is equal to 0.8 pi epsilon naught coulomb. So once we have been decide the value of Q here, so we just put the value of Q in this expression, then we will have the general expression given by the expression that represent our electric field intensity vector of E given by this formula. Then if R is equal to 2 meter and theta is equal to 90 degree, so if we put all this value inside this equation, then we will have the vector of electric field intensity by considering this vector is given by this expression, whereas equal to theta cap quarter millivolt per meter. So that's solution for question number 16. Okay, good luck. See you again, and thank you very much.